Hey everyone, so today we're going to be talking about the synthesis and reactions of carboxylic acids and nitriles. Again, grouping these together because a lot of times they have similar chemistry to each other. So in the past, we have seen some reactions that create carboxylic acids, like the oxidation of a primary alcohol, right? Which just means that we have a OH group attached to a first degree carbon. So this is a primary alcohol, and in strong oxidizing conditions, we will eventually create carboxylic acid, first oxidizing to an aldehyde and then to a carboxylic acid. And remember, this is the addition of carbon oxygen bonds and the subtraction of carbon hydrogen bonds. That's how we can think of oxidation and reduction in this context. We can also do a hydration reaction, right? So if we have an alkene and we add heat and acidic conditions, so H3O plus, we can then cleave the alkene and create two carboxylic acids as well. If we do not have the heat, so with no heat, this will create a diol like this. And so the heat is important because the heat is actually what allows us to oxidize the diol even farther into a carboxylic acid. And the last one is we've looked at the basically replacement of a second degree halogen. Sorry, not a second degree halogen, but a secondary alkyl group, which is what we have right here on a secondary carbon. Right, so a second degree alkyl group, we replace it with a cyano group, and then from there we can create a carboxylic acid using strong basic conditions, water, and then an acid added in the second step, right? Because the first step is going to create the carboxylate ion, then we add H3O plus, and that creates our carboxylic acid, right? As we drop the pH, we're more likely to see the protonated version of the carboxylic acid. And this last kind of general step of going from a second degree alkyl halide to a carboxylic acid, this is the important in the synthesis of ibuprofen, actually. Synthesis of ibuprofen. And so this, one other thing noting here is that we actually end with an extra carbon atom in this compound right here. This carbonyl carbon, or the nitrile carbon, is an extra carbon there. And so the general theme for synthesizing these carboxylic acids is strong oxidizing conditions, right? So we have strong oxidizing conditions because we're trying to create carbon oxygen bonds, and a lot of times to do that we're removing carbon other types of atoms, usually carbon hydrogen bonds as well, if we're going to two hydrocarbons. So the first, or another type of interesting way to form a carboxylic acid, is from a Grignard reagent, right? And so what happens is if we bubble CO2, so this is gaseous CO2, and then we have strongly acidic conditions. Again, this is usually just because we're going from our carboxylate ion to the carboxylic acid version of the protonated version of the carboxylic acid. That's usually why we add acid at the end. This is another way that we can synthesize a carboxylic acid. And so our Grignard reagent, for example, if we have RMgBr, we bubble carbon dioxide over this. This oxygen is extremely electrophilic in the carbon dioxide, and so this will be attacked by the Grignard reagent, which will then create the carboxylate ion, right? So now we have this, one of the electrons from this pi system here move on to the oxygen. One of the oxygen atoms creates carboxylic acid, and then we add the H3O plus to then finally create a carboxylic acid. And this is a popular way in the synthesis of aspirin, right? So in the synthesis of salicylic acid, we can bubble, and this is usually a lot more efficient than synthesizing this on a benchtop in the lab, bubble carbon dioxide over a benzene derivative to then create salicylic acid. So we can create we can create carboxylic acids from the synthesis or from granular reagents as well. And so granular reagents are one of these things that we've seen pop up in a number of different functional groups and are used actually pretty widely in a lot of different interesting chemistry, even today, even though the granular reaction was founded a long time ago. The reactions of carboxylic acids are both similar to both alcohols and to carbonyls, right? The aldehydes and ketones that we have talked about before. And so specifically, we've talked about, using reduction as a method of starting from a carboxylic acid and moving towards an alcohol, right? So this is the direction of starting from a carboxylic acid, and then we create an alcohol, or we can create an aldehyde, perhaps. The deprotonation, so this is acid-base reaction. This is similar to other acids. This would be adding base or adding acid is the deprotonation, so that's protonation of the carboxylic acids. In these last two, the alpha substitution and nucleophilic acyl substitution, right, we're replacing this OH group with another group that gets added to the acyl group or aryl group here. That's something that we'll be talking about when we talk more about the carboxylic acid derivatives in probably the next couple lectures that we'll be talking about that. And so that's all we'll talk about now for the chemistry of carboxylic acids. We'll start talking about the chemistry of nitriles now, and there's going to be a lot more reactions involving carboxylic acids, and we talk about their derivatives and things like esters and hydrides, and then like we've done in lab, different condensation reactions involving this interesting carbonyl chemistry. To carbonyl carbons, the nitrile carbons are strongly electrophilic as well. So these are also electrophilic because we have this electronegative nitrogen that creates a dipole that puts a partial negative on the nitrogen in the cyano group, right? And so a carbonyl carbon, when we talked about carbonyl chemistry with the aldehydes and ketones, forms an sp3 intermediate or tetrahedral intermediate from the sp2 carbonyl carbon, and then that would be the intermediate step to then looking at our nucleophilic substitution reactions a lot of times for aldehydes and ketones. Similar to that, a nitrile forms an sp2 intermediate, imine. So imines from the sp carbon in the nitrile, right? So in the carbonyl chemistry, we had, our R group, and then let's say it was a ketone, for example, and then when we had a strong nucleophile attacking this, we would create, this would attack the carbonyl carbon, we would have our nucleophile then create this tetrahedral intermediate. All right, so this was our tetrahedral intermediate that was created from the nucleophilic attack. Oops, sorry, this should be just a minus charge here. The nucleophilic attack of the electrophilic carbon. In the nitrile chemistry, it's going to be similar, except instead we'll have the nucleophilic attack of this nitrile carbon, and instead of an sp3 tetrahedral intermediate, so sometimes you'll see T sub H to be tetrahedral, we're going to create an imine intermediate, and also it's going to be an anion as well, just like the tetrahedral intermediate was for the carbonyl carbon, with an sp2 intermediate, right? So a trigonal planar intermediate anion. This would be trigonal planar. And so this is going to be the intermediate step that then gets used to produce the products in nitrile chemistry a lot of the time. All right, so we go from a linear carbon atom to a trigonal planar carbon atom, and that's our intermediate step for a lot of these nucleophilic addition reactions. So a lot of these reactions that I'm looking at now, these common reaction nitriles, fall under this same general type of mechanism, right? So we can have hydrolysis of the nitrile, right? So we add water to the molecule. So you see That's why this is called hydrolysis. We have two H's and an O added to the cyano group here, and that's why it's called hydrolysis. And then this can then be further reduced to then form a carboxylic acid. This is another method going from what we would say a primary amide. We haven't talked about amide and amines yet, but this is a primary amide to then form a carboxylic acid. So you can do that using this methodology as well. Then we can also have the reduction of a nitrile, right? So we're reducing this nitrile. We're adding carbon-hydrogen bonds, right? So here we have no carbon-hydrogen bond, and here we have two carbon-hydrogen bonds. So that's why this is called reduction, right? We can think of reduction in this context here. We see reduction happening here, and that's with a strong reducing agent like lithium aluminum hydride. And then the last thing we'll talk about is also similar to carboxylic acids. We can use a Grignard reagent to then create a ketone. Right, so we use a Grignard reagent to then create a ketone. And a lot of the time these reaction mechanisms are going to be similar to the nucleophilic addition of a carbonyl carbon, except this is going to be a nitrile carbon that we're looking at. First one we'll talk about is a hydrolysis of nitriles. And so following the theme of nitrile chemistry that we just talked about, we'll have the nuclear addition of an anion to the very polar nitrile bond, right? And so that creates an electrophilic carbon, which can then is susceptible to nucleophilic attack. And so the general mechanism for this is going to look something like this. We have in our hydrolysis, this is usually going to require some strong base for this to happen. It can require an acid to create the same effect. So you can have this acid or base catalyzed. And so we have our base, our hydroxide ion floating around in solution, which can then act as our nucleophile in this case. So there is our arbitrary nitrile, and we get nucleophilic attack of the nitrile carbon and then move the electrons from the pi system onto the nitrogen here. And then we create our sp2, and this is going to be hydroxide in this case, or hydroxy group. We create our sp2 imine intermediate, right? So this is going to have a negative charge. So this is our sp2 intermediate. Then if we have water floating around solution, right? So we have a water molecule here, then we can regenerate our base in this case by having this nitrogen abstract this proton, and then we recreate our hydroxide ion. So we have R, N, C double bond to the N. Now there's no more negative charge here. We have our imine, except this isn't our imine. This would be the anion. Then we have our imine intermediate now, except this is not an anion anymore. There's our protonated imine. And then we can have the addition of, essentially happen is we get an imine amide tautomerization. And so if we have our base around here floating around in solution, right, so here is our base in solution. This can basically abstract a proton from this OH group, the hydroxyl group, on the imine carbon now, right? So this can abstract protons. This is very similar to the enol keto tautomerization that you've seen before, right? So you have an enol, basically a hydroxy group, on the next to a double bond, an alkene, and you move the proton over and you can create a ketone. So this is going to be similar to that. So we
abstract this proton here, and we abstract this proton, this allows us to go through this tautomerization where we're going between. So this happens, we're moving between these. We have this minus charge on this oxygen now, this lone pair here. And what can happen is then we move the electrons into the bond between these two, and simultaneously we put a minus charge on this nitrogen now, and these two are interconverting between the two. So it's similar to aldol condensation, how we had to generate the enolate ion from adding a strong base to the solution. And so now we have a carbonyl group here and a minus charge on this nitrogen. And so this right here is the result of this hydroxide abstracting this hydrogen here. And so I'm going to go to the next page now, because once we have this, right, so I'm going to rewrite exactly what I just wrote. So, right, so we extract this hydrogen, we have a carbon double bond O right here, and our R group up here, this moves here. The electrons move up onto the nitrogen. This is our after our tautomerization, after the deprotonation step of our tautomerization. Two lone pairs of the nitrogen now, so we have a minus charge and a carbonyl group here. And so now that we have this floating around in solution, this can then abstract a hydrogen from water. And when that happens, this will then generate our primary amide. All right, so this is our primary amide. And once we have our primary amide, we can then add acid to this to then oxidize this further to then generate our carboxylic acid, right? So we can generate a carboxylic acid using this this chemistry here, this actual specific reaction a little bit more when we talk about derivatives of carbonyl chemistry, right? So this is our carboxylic acid. Basically, we go through even further hydrolysis for this to happen, right? So what happens here is we generate this imine intermediate that then goes through this tautomerization process that we just talked about. Tautomerization is basic structural isomerization where there's two interconvertible forms, right? So we're going from this imine to this then amine in between these two, and these two versions by adding base to this solution. Right, so this is how the hydrolysis of a nitrile works to then create a primary amide, which then can be further hydrolyzed to then form a carboxylic acid. The next reaction we'll look at is the reduction of nitriles. And so similar to how carbonyl groups get reduced to alcohols, nitriles get reduced to amines, right? Because we're breaking carbon-oxygen bonds or forming carbon-hydrogen bonds, right? And so if we have our nitrile group here, and we put this in strong reducing conditions, like lithium, aluminum hydride, we should then form, because we don't have carbon-oxygen bonds to break here, we should form carbon-hydrogen bonds, which are what I have highlighted right here. These are new carbon-hydrogen bonds, and then we have an amine as the other substituent group here after reducing the nitrile into an amine. What happens in these cases is we get the reduction after adding. So let's say after plus lithium aluminum hydride, we get there may be one step of reduction here, and we have a negatively charged nitrile or enamine anion, right? So we have reduced in one step here. Now we have a minus charge, And the base, or basically the Lewis base that has been created by the aluminum hydride, for example, so this can be any AlX3, for example. When we do these reductions, they generally abstract one of the halogens or something along that nature. And this stabilizes this imine anion, which then when it gets reduced even further, where we now have a -2 charge on this nitrogen here, is stabilized by the very, very electron poor aluminum in this compound. Step here that has both of the stabilization of this dianion just because it's dianion just because it is a -2 charge. The stabilization of this dianion by this Lewis acid Lewis base pair aluminum compound. This stabilization, we wouldn't get the full reduction of this compound, this nitrile, unless we had the stabilization from these here. Surrounding and being surrounded by water can then be protonated to then produce our primary amine in this case. And so just to, in case we've forgotten, the mechanism for the reduction or the nucleophilic addition of hydride, right? So if we have a strong reducing agent like lithium plus and then aluminum hydride, all right, we know that this is going to be very negatively charged here. And if we have, we'll use the example of a carbonyl nitrile, but this is also the same when we have a, sorry, not a carbonyl nitrile, a nitrile carbon is the same as if we have a carbonyl group. The mechanism is exactly the same here, is that you're going to get nucleophilic attack of this bond here to the nitrile carbon, which will then move the electrons from the pi system up, which will then create our anion intermediate here, which is stabilized by both the positively charged lithium and the aluminum H3 compound here, right? And so this is stabilized by both the positively charged lithium here and this compound here. And we won't go through the mechanism again, but the idea is here, for example, if we had a, we're also missing a hydrogen here now. If we had water surrounding this, let's say that we didn't have full stabilization, and then we were to reprotonate this nitrogen right away. CrH here, it's minus charge, lithium plus. This will then abstract a hydrogen from water molecule, and then we'll create lithium hydroxide as a byproduct, right? And so this would create our, if the reduction stops right here, this would create an imine intermediate, which is something that we've kind of seen before with the nucleophilic addition of hydrazine to aldehydes or ketones, right? And so this is the same mechanism. If we had one more step that worked here, we would just, instead of having only one step of this first nucleophilic addition of a hydride, it would be in 2 steps here, right? So that's how this mechanism to then create our primary amine actually works, right? So if we have strong reducing conditions, we reduce nitriles into primary amines, right? So this is a primary amine. And so the last reaction we'll talk about is the reaction of nitriles with Grignard reagents. So Grignard reagents, like I said, important for a lot of important reactions in chemistry. and are used widely in both industry and academic labs these days. Bullet point was for the previous slide and not for this one, so I'll cross that out. The basic idea of this is it's the exact opposite of the hydrolysis of imine formation that we talked about last chapter. So the mechanism of the hydrolysis is the exact reverse of the imine formation that we saw last chapter, right? So when we did the imine formation with hydrazine, for example, this is kind of the reverse of that reaction. So if we have our nitrile and our Grignard reagent, R prime, MgX, I was going to put MgBr, but it could be any halogen, R prime. This is going to attack the very electrophilic nitrile carbon and create our imine sp2 intermediate. And this is an imine, right? This is our sp2 intermediate here. And then with the presence of water, this can then be protonated to then form an aldehyde or ketone. And the byproduct is ammonia in this case. All right, so this plus the addition of water, which is then, this is the opposite, this step right here is the opposite of imine formation of ketone or aldehyde. Now we'll talk about that hydrolysis really quick, since it is the opposite of when we had the imine formation from an aldehyde or a ketone. All right, so we start off with our negatively charged sp2, sorry, not negatively charged, we'll do after we've added water, so our neutral imine compound, R and R prime. We have the presence of H3O plus, which is then going to protonate this nitrogen, right? So remove the lone pair here just so it's easier for it to attack the proton in the H3O plus. So then we get C, R, R prime, double bond, and R, H, H. And now this is going to be positively charged. We then have the presence of water in solution, which will then attack nucleophilically this imine carbon, since it is a polar bond, and that will be electrophilic. And then this will move the electrons from the pi system between the carbon and nitrogen onto the nitrogen here, and we'll have a basically a tetrahedral intermediate with an amine. This is going to be NH2 up here. We'll have R and R prime here, and then our positively charged H2O, which will then be deprotonated by another water molecule to regenerate our acid catalyst. And then when that happens, simultaneously have another protonation of the, sorry, this arrow should be going the other way. Another protonation of the amine group here. This creates, still tetrahedral intermediate. So now we have NH3 plus here, OH, R prime, R, and then we basically get the movement of these electrons between the carbon to form carbonyl, and then the abstraction, the NH3 plus, is a good leaving group now. So then this is abstracted from the compound. Water, once this compound is going to be, so now we have lost that, is going to look something like H with a positive charge here. Water is going to regenerate the acid catalyst by abstracting this proton. And then we have our aldehyde or ketone here in this last step. And so this is how the reverse hydrolysis of the imine. So last time aldehydes and ketones is the nucleophilic addition of hydrazine to, or just a secondary or primary amine to an aldehyde or a ketone that could then produce an imine. In this case, it would only be a primary amine that would create a imine. Secondary amines create the enamines. This is the reverse hydrolysis where we get an imine intermediate, and then we can then hydrolyze that to then create an aldehyde or a ketone. Okay, so that was the last thing I want to talk about for this lecture. So this is the more focused on kind of the specific reactions involving nitriles, because carboxylic acid derivatives will go into a lot more detail, specific reactions involving carboxylic acids.